I'm Peter Adamson, and you're listening to the History of Philosophy podcast, brought to you with the support of the Philosophy Department at King's College London and the LMU in Munich. Online at historyofphilosophy.net. Today's episode, The Eye Sees Not Itself, but by Reflection. Theories of Vision. You can tell a lot about a historical period from the examples given by its philosophers. The medievals loved to devise thought experiments invoking their omnipotent god. When Kant and other German philosophers deal with aesthetic experience, they speak of the awesomeness of nature, a good fit for the literary culture of the day. What it says about our own time that philosophers cannot stop talking about killing people with runaway trolleys, I'll leave you to judge. Back in antiquity, philosophical illustrations were a bit more wholesome. The standard example of a visual illusion, used already by Plato in his Republic, is that something straight, a wooden rod, say, will look bent if it is half submerged in water. For centuries thereafter, philosophers mentioned the apparently bent stick, but without being able to explain why it looks bent. The answer, of course, is that although the stick is not bent, the light coming from the stick to your eye is bent, or refracted, by the water. One is tempted to say that the water refracts the light, whereas air doesn't, but that's not quite right. Air refracts light too, just not as much as the water does. The difference in the refractive index of the two different media explains the illusion. As I mentioned last time, Thomas Harriot was keenly interested in this phenomenon, and by 1601 discovered a general physical law to characterize it. It's now called Snell's law, not Harriot's law, since as usual he only wrote it down in his unpublished manuscripts. Actually, Descartes was the first to publish a proof of the law in 1637, after the result was publicized the previous year by his friend Mersenne. It's also called the sine law of refraction, since it allows for the calculation of the refractive index by dividing the sine of the angle at which light strikes the medium by the sine of the angle of refraction. If you'll pardon the expression, there are some striking parallels here, namely with Harriot's work on specific gravity. As in that case, he needed to do careful observations with different materials to get a constant for each substance. With specific gravity, that meant weighing samples in air and water. Here it meant putting objects with markings on them into water and measuring the apparent positions of the markings compared to what he knew was the real position. He calculated his results out to 6 figures. This was rather a case of overkill, since his actual observations were not so accurate as to bear this level of precision, but it shows how carefully he was proceeding. And there was another parallel to the specific gravity research, namely that the work on refraction was highly useful. Specific gravity was important for weighing metals, like gold and silver. Refraction was important for something Harriot might have seen as even more crucial, namely astronomy. Since air does bend light too, the real positions of stars seen through our atmosphere would need to be recalculated by correcting for refraction. I just said that Harriot failed to convey this information to the world, but that's putting it mildly. He even deliberately concealed it. Like someone weighing precious metals, he had a golden opportunity to reveal the sine law when he entered into a correspondence with Johannes Kepler in 1606. This was prompted by his reading of Kepler's own work on optics, published 2 years earlier. Though Harriot was apparently in no hurry to share his law with the world, he apparently wanted to make sure that no one else would do it first. The exchange between them was ultimately frustrating, especially for Kepler. Harriot sent him only enough information from his own observations to disprove Kepler's preferred theory, which was that the index of refraction simply correlates with density. Kepler was persuaded that his guess was wrong, and badly wanted to know the real formula. "Now you," he wrote to Harriot, "excellent initiate of the mysteries of nature, reveal the causes." True to form, Harriot refused to do this, though he gave a hint at his own understanding when he teased Kepler, "I have now led you to the doors of the house of nature, where her secrets lie hidden. If the doors are too narrow for you, then mathematically abstract and contract yourself to an atom, and then you will easily enter. Later, when you leave, tell me what marvels you have seen." This suggests that Harriot wanted to explain refraction in terms of an atomic theory of matter, and that is confirmed by the work of Nathaniel Torporley, a fellow member of the Northumberland Circle. Harriot thought highly enough of him to make Torporley his literary executor. But as Aristotle once said when criticizing Plato, truth is more dear to us than our friends, and Torporley didn't hesitate to dish out some heavy criticism of Harriot's atomistic explanation of refraction. Think again about the body of water with an apparently bent stick in it. You might also see sunlight reflecting off the surface of that water, which shows that the water is reflecting some of the light while letting other light through, with the latter being refracted. Harriot's idea was apparently that the reflected light is bouncing off the top layer of atoms that make up the water. The refracted light, meanwhile, filters through the atoms of the body and in the process is deflected as it seeks a path through the empty spaces between these atoms. One of our former podcast guests, Robert Goulding, has aptly called this a zigzag through a pinboard account of refraction. Torporelli found it unconvincing. For one thing, the many rays of light should be bouncing off the atoms in all directions and not filtering through at just one angle all the time. For another thing, the refracted light that passes through the body somehow takes on its color. A stick in water may look somewhat blue, for instance, in addition to looking bent. If the physical makeup of bodies was controversial, the nature of light itself was still more mysterious. Astronomers like Harriot had every reason to concern themselves with this problem, since the only way for them to study the heavenly bodies was by means of the light that comes from them. The phenomena of parallax and refraction are just two examples of the way that optics and astronomy went hand in hand. Hence Harriot's investigations in both fields, but no one from the period illustrates the point better than his exasperated correspondent, Kepler. His work on optics represented a significant shift in the philosophy of light. Here, at the turn of the 17th century, the state of the art was still quite literally medieval. The most advanced account of light had been produced by the Muslim scientist Ibn al-Haytham, known in Latin as Al-Hazen. His works were used by a medieval author called Witello. Writings of both men were available in print by the time of Harriot and Kepler, thanks to the Thesaurus of Optics published in 1572 by Friedrich Risner, a student of Peter Ramus. The account that Harriot and Kepler could find in these texts took distance from Aristotle's theory of light and vision without fully abandoning all his ideas. For Aristotle, light simply enables a transparent medium to transmit the image of a visual object to the eye. By contrast, for Ibn al-Haytham, light is propagated along straight lines from light sources and then from the surfaces of the other bodies they illuminate. Imagine that I am looking at a giraffe standing in a pond, wondering why its legs look bent, or rather, even more bent than usual. Aristotle would say that the light suffusing the air between me and the giraffe activates the capacity of the air to bring to my sight an image of the giraffe. One way to think about this is that the illuminated air is indirectly putting my eyes in contact with the giraffe, because my eyes are touching the air, which is touching the giraffe. This solves the problem of how the giraffe could be causing me to see her, even though she's all the way over there. If the sun goes down, I will stop seeing the giraffe, which for Aristotle is simply because without light, the air loses its ability to connect eyesight to its object. Ibn al-Haytham and Witello would instead say that rays go from the sun to the giraffe and then to my eyes. There are many advantages of this account over that of Aristotle. For starters, it seems to explain mirror images better. It can also account for the fact that I can see a luminous object through dark air, like a giraffe at nighttime decorated with Christmas lights. Well, how do you celebrate the holidays? Finally, this idea of light as consisting of rays lends itself to a geometrical analysis of optical phenomena. You can imagine the rays spreading out in a cone from each luminous point, with the light strongest along the perpendicular line through the center of the cone. Still, the upshot of the whole process would be much as Aristotle thought. An image of the giraffe comes to my eyes, conveyed by the luminous rays. Kepler agrees with a lot of this, especially the idea that we can represent light mathematically. However, he sees light in more physical terms. He says that a ray is nothing but the motion of light itself, and understands the light as a physical phenomenon that can, as it were, bounce off objects when it is reflected. This is not to say that light is a body or that it moves across space bit by bit, like flowing water. Rather, it traverses the entire space instantly and is a kind of compromise between material bodies and immaterial things. Kepler thus calls light the chain linking the corporeal and spiritual world. As this remark reminds us, Kepler was a committed Platonist, albeit a rather unorthodox one. We can see this from his discussion of the sun, which is influenced by an equally unorthodox Platonist, Nicholas Cusanus. Inspired by Cusanus's comparison of God to a sphere, and of course by Copernicus's heliocentrism, Kepler sees the sun as nearly divine. At the center of all things, it is the seat of the soul of the universe, and diffuses both light and life. All other things that participate in light, he says, imitate the sun. In a significant break from the previous tradition, for Kepler, what comes to the eye from the sun, from other light sources, and from the things that they illuminate, is not an image of what is seen, what was called a visual species in medieval Latin. The only species involved is light itself, which is noted by Torporley can absorb color from the surfaces it has visited. Or actually, that isn't quite right, because we can also see the absence of light. The study of the stars frequently involves seeing shadows or obstructions to light, for example, when observing a solar eclipse. This is why Kepler says that the things to be considered optically in astronomy are the things themselves, set before the sense of sight, by way of considering the species of things, that is, light and shadow. It's worth dwelling briefly on just how Kepler might have gone about observing a solar eclipse. As you've surely been warned if you've ever had the chance to see one, you should not look straight at it. Instead, as amateur stargazers do today, Kepler would have used an apparatus with a pinhole. It allows through a small amount of light, projecting the image upside down onto a screen. Just as on Kepler's account of vision, light falls on the retina of the eye to create the image that we see. The larger version of this device is called a camera obscura, with light allowed through an aperture into a darkened room. Kepler was very interested in the phenomenon. He once set up an illuminated book in front of a pinhole camera and led taut strings from its edges to the images of the projected image, running through the aperture. This helped him to prove that any distortion caused by the apparatus, for instance by the size or shape of the pinhole, could be explained and corrected through geometrical analysis. For example, he could show why a triangular aperture would, at a certain distance, throw a circular rather than a triangular image of the sun, something that the medieval optical texts could not easily account for. All this served the same goal as correcting for the refraction of light in air when observing the heavens. Kepler wanted to use optical theory to improve the accuracy of astronomical data, so that the science of the stars could be put on a more confident footing. But as brief reflection will show, all the ideas we've just been discussing could just as well disturb our confidence in vision. The idea that I am not seeing that giraffe or even an image of the giraffe, but merely the light coming from the giraffe, is already somewhat disconcerting. In Kepler, we can find telling turns of phrase pointing in that direction, as when he describes observing the moon through a camera obscura and says the moon's ray was in the paper. And that's without even getting into things like mirror images, parallax, and the pervasive refraction of light. The more you think about this, the more you might start to suspect that you quite literally cannot believe your own eyes. Which brings us to an interesting book by Stuart Clark that appeared in 2007 called Vanities of the Eye. It catalogs the many reasons that early modern people started to distrust the visual experience. Some of his examples are already familiar to us. When discussing Macbeth, we saw that demonic influence could cause people to see things that aren't there, for example, a dagger floating in the air. Such illusions were especially associated with demons because, as I mentioned, these malevolent forces have no bodies and can only manipulate us through images. As one author of the time put it, the devil works his effects only by the delusion of the eye. We also saw that a more natural explanation could be given for the same sort of phenomena, namely melancholy. This disease could affect the imagination by unbalancing the humoral mixture of the brain. So, the delusional melancholic would actually be seeing things prompted by an internal disturbance rather than an outside cause. This might help to explain why the enthusiastic visions formerly appreciated as religious experiences were now more apt to be greeted by suspicion. In the early 15th century, Marjorie Kemp could convince a good number of people that she was seeing Christ, even if she also ran into a fair bit of skepticism. Now, around the year 1600, she'd more likely just be diagnosed with melancholy, or charged with witchcraft, or both. Another important factor in explaining that change was, of course, the Reformation. The Protestants dismissed all supposed modern-day wonders, with one author remarking that they were miracles in sight, but in deed no miracles. More generally, they tended to value the auditory over the visible. Godly people listen to the Bible being read out to them. They don't hope to see angels or feast their eyes on statues of saints dripping with blood. Luther put it with his characteristic bluntness, "Do not look for Christ with your eyes, but put your eyes in your ears." The general attitude on this side of the religious divide is captured well in the book that gives Clark the title of his own study, George Hakewill 1608 treatise, The Vanity of the Eye. Hakewill was a Calvinist theologian and college rector at Oxford. This work, which he wrote for a blind friend, attacks eyesight from every conceivable perspective. It is subject to mistakes due to everything from optical illusions to illness, sorcery, and demonic possession. It is also associated with wicked desires, like lust, and worst of all, it's associated with Catholicism. Now, as Clark notes, this is rather an oversimplification. Catholics could be, and were, accused of an overly visual culture of worship. Their churches, untouched by the purifying bonfire of iconoclasm, were full of images of those bleeding saints and the suffering Christ. In their ceremony of the Mass, the priest would dramatically lift up the host for the congregation to behold. But according to the Catholic understanding of this miraculous event, there is a clash between the appearance of the sacrificial host and its real nature. It looks like bread, but in fact it is Christ's body. So in this case, it was actually the Protestants, or at least some Protestants, who insisted that what you see is what you get. The bread really is what it looks like and merely symbolizes Christ's body. Indeed, on their view, this is the whole idea of a sacrament. One thing stands in for or represents another. Still, the point stands that the Protestant trend towards an anti-visual culture reinforced other cultural forces that were undermining trust in the senses, and especially vision. The logician Thomas Wilson, whom I mentioned a couple of episodes back as the author of a work on logic in English called The Rule of Reason, once wrote that the eyesight is most quick and containeth the impression of things most assuredly. But increasingly, there was good reason to fear that eyesight is too quick, that it leaps to conclusions and misleads us. Clark therefore connects this theme with another trend of the time, namely the rebirth of philosophical skepticism in authors like Montaigne and Charron. It may not be a coincidence that Hakewill, author of The Vanity of the Eye, was an admirer of Charron's treatise On Wisdom. At first glance, it might look like the optical research done by Harriot and Kepler fits into that picture. Just as an inner force like melancholy or demonic possession might deceive you from the inside, so a curved mirror, or the refraction of light, might deceive you from the outside. Even more potentially disturbing was Kepler's claim that we only ever see light, not the actual light sources or illuminated objects, and light can be manipulated, as with John Dee's famous trick mirror, which he used to amuse the Queen. Protestant debunkers exposed charlatans who created miraculous auras of light using mirrors, and Kepler himself told of playing a trick on friends, where he used the camera obscura technique to make it look like magic Hebrew letters were dancing on the wall. But the association of optical advances with skepticism should itself be treated with a bit of skepticism. Sure, the science of light and vision could be used to play tricks, but that was not the real goal. As I've said, what Kepler and Harriot really wanted to do was put themselves in a position to correct for optical effects, especially when doing astronomy. Their project was thus to use mathematics and measurements to free the scientists from illusion and distortion. The implicit message was not, you can't even trust your own eyes, so who knows what to believe? It was, you can't trust your own eyes, but you can trust geometry. So while 17th century skepticism does bear some relation to what we've been discussing, 17th century mathematical science was the real inheritance of Kepler, of Harriot, and the rest of the Northumberland Circle. They were forerunners of the Descartes who did things like explaining the rainbow and inventing a coordinate system to represent space, not of the Descartes who invented the evil demon hypothesis. Vision would continue to be the central illustration of science's potential to raise skeptical challenges and then answer those challenges. Just think of the way that telescopes and microscopes would be revealing truths of nature that are hidden from normal human sensation. Yet again, from this vantage point at the end of the 16th century, we can glimpse fleeting images of what was yet to come. In this episode, our focus was on what can be seen, even if it isn't seen accurately, but scientists of the time were also thinking about the invisible forces of nature. We aren't yet ready to talk about gravity, as we will when we get to figures like Newton, but next time we have an equally weighty subject, magnetism, and the breakthroughs made in understanding it around the turn of the 17th century, especially by William Gilbert. That's what will be attracting our attention next time here on The History of Philosophy, without any gaps.